In this work, we explore the possibility of improving upon an existing robot hardware configuration to make it more efficient at task performance and learning. Learning has been one of the most promising tools for operating robots in unstructured environments, enabling them to acquire complex perception and reasoning capabilities. However, the current robot design practices overlook the impact of perception and design choices on robots' learning capabilities. For example, robot morphology can interfere with the robot's visual sensor and prevent it from observing critical task-specific information, leading to a degraded robot learning and performance. Such scenarios motivate us to explore the hardware optimization without neglecting the interplay between the robot's design, onboard perception, and their interaction in different tasks. To address this challenge of robot design optimization for vision-based manipulation, we present a learning-oriented morphology optimization framework. Our key idea is to develop a morphology-agnostic controller that is capable of controlling a range of morphologies using onboard visual observations. The controller is trained using a privileged single-stage learning via alignment formulation, which unifies the typical two-stage learning of teacher and student into a single stage. Once the morphology-agnostic controller is learned, we optimize robot design parameters using sampling-based optimizer, and morphology-agnostic controller performance as a surrogate measure, greatly reducing the cost of traditional two-loop design optimization. Let us first look at the morphology-agnostic controller, or shortly, MAGIC. MAGIC is a key component of our learning-oriented morphology optimization framework. MAGIC uses robot onboard information and information about the robot morphology to generate the robot actions. The MAGIC policy is trained to control a wide range of robot morphologies and tasks. To train MAGIC, we introduce privileged single-stage learning via latent alignment, or shortly PRISM framework. The architecture of PRISM consists of two main components: an onboard information encoder, a privileged encoder, and a policy head. Onboard and privileged encoders are explicitly aligned during training using alignment loss. To regularize the network and make it robust to occlusions from different robot morphologies, we use image augmentation during the training process. This approach ensures that MAGIC can control various robot designs effectively and realistically based on its own observation capabilities. The PRISM framework unifies the typical two-stage approach of teacher and student training into a single stage by using a latent alignment loss during the optimization process. This approach allows us to discourage the MAGIC policy from learning supernatural behaviors, which incorrectly exploit the information only present in privileged states. As a result, the policy learns behaviors characteristic of its own vision-based observation capability. Next, we use MAGIC policy during the design performance evaluation and the hardware design optimization loop. Since the MAGIC policy is primed to disregard the occlusions in onboard observations, it can be used to control a range of robot designs and provide a surrogate measure of the robot design performance. Such approach eliminates the need for per-design training and greatly reduces the cost of traditional two-loop design optimization. To understand the trade-offs between the morphology-agnostic and targeted controllers, we compare their performance on human expert-made and MAGIC-optimized robot designs. Target controller in this case is trained from scratch using robot-specific data. We find that with MAGIC-optimized design, the performance of MAGIC and targeted controllers is almost identical. On the other hand, there is a large gap in performance on human-made robot design. Next, we compare these robot designs in their task performance and learning efficiency. We find that MAGIC-optimized robot requires 25 times less data to match the human expert-made morphology performance. Additionally, an improved design leads to a 19% overall performance improvement when given access to the demonstration buffer. Lastly, we investigate what effects does an increased number of tasks has on the robot design. We repeat our experiments on more complex manipulation tasks and find similar overall performance improvements when compared to the human expert-made robot design. We also find that multitask training produces a more regularized robot design with shorter and more manageable links that are likely easier to manufacture. In summary, we propose a cost-effective method to improve the robot hardware by training a morphology-agnostic surrogate controller, and demonstrate that a robot designed with learning considerations can excel at learning compared to a human expert design. We hope this work contributes to the growing trend of learning-based robots and sheds light on opportunities in hardware design that facilitates better learning.